It's 10 o'clock, so we're going to start the webinar on time. Well, welcome to those who are here already. This is number 6 in our webinar series on nitrous oxide emissions from wastewater treatment. Over 300 people have signed up for this edition from all over the world, which really goes to show how in the last few years this topic of nitrous oxide process emission has risen in importance and has become very urgent on professionals' agenda. So I think it's a very good moment that today we will look at some of the large-scale monitoring campaigns that are happening throughout the world, especially in some of the front-running countries, and that we can learn how and why these measuring campaigns were designed and what the data can be used for as well. Yes, we're very lucky, and I'm very thankful for the great presenters that are with us today and that have dedicated their time to prepare their presentations and be on the meeting. We have 3 great speakers with a lot of experience from Denmark, from the Netherlands, and from the UK. And yes, again, very thankful that they want to share their experience with the professional community today. Each of the presentations will be 20 minutes with a dedicated Q&A session of 5 minutes after that. And then we will start and end the meeting with some short polls to have an interactive element with the audience and learn something from all of you who are listening as well. A little bit of housekeeping to keep this meeting focused, sharp, and respect everyone's time with the large number of participants. We decided to keep the cameras, the microphones, and the chat locked. The chat will be open in the beginning. If you have any technical problems, you can write them in there. But once the presentation starts, we will have the chat locked. Just to keep the focus on the presentation and to keep the focus on the Q&A session. For asking your questions, you can use this Q&A button, which you have next to your chat. Write your question in there, and then we will take it directly with the presenter at the end of the presentation. As I said, we will have a couple of polls, and they will just start automatically, should be popping up on your screen. If they do not do that for any reason, have a look into the chat. Then you should find the poll there, and you can also find the answered polls in there to look up the answers later. And also, yeah, just practically, we will share a recording of the whole session as well as the slides from all the presentations afterwards by email. So there's no need to take any screen pictures during this session. Yes, with that, I'm just going to go into the first poll. We already have over 100 people joined in the meeting, so that's great. The poll should be coming up for you. Basically, it's just to get to know the audience who's here today, to get an understanding which sector do you work in. Is it a utility, consulting company, academia, or policymaking? So please just give us a quick idea of who you are and then click submit. And yeah, I can see we have a good number of responses already. We have a large number of utilities joining, almost 50%. So that's great to know. A lot of the practitioners are here today. Fantastic. That's very interesting. And then to our next question. This is about the awareness of other professionals, people besides you in your sector or in your region about the topic of nitrous oxide process emissions. Would you say you're more a lone wolf in your fields, in your company, in your sector, or is there already a broader awareness of the importance of nitrous oxide to greenhouse gas emissions from a wastewater treatment plant and interest in the topic? So we can see, yeah, about 50% saying there's basic knowledge. That's really great. 40% even fully aware. I think if we asked this question 2 years ago, the answer would be completely opposite. So that is really, really great to see from you guys. So thanks very much for your responses. And well, with that, I will hand over to our first presenter, which is Mikkel Stokholm-Bjerregaard. He is the head of innovation in wastewater at the Danish consultancy Veolia. And well, he's been deeply involved with diverse projects on nitrous oxide monitoring, modeling, process emission mitigation. So today he will present on the big picture from a Danish perspective and on the work that that Krya is doing in that field. Very thankful that you're here with us today, and floor is yours, Mikkel.
Thanks a lot, Bastian. And I hope now I'm sharing my right screen and all works well.
Looks perfect.
Okay, thanks a lot. I'm happy that a lot of the participants in this webinar actually already has been interested in the subject of nitrous oxide emissions for some while, because I realized I did not include any introduction to that in my presentation, but decided to jump straight into the point of this presentation right here. And I will start by presenting some of the work that we have recently done from the Danish EPA on preparing future regulations on the area. And just as a disclaimer, I just want to make sure everybody knows that this presentation that I offer here today offers a perspective on how to implement regulation of N2O emissions, and is not the final regulation. Nor does Krya have or Veolia any influence on the actual legislative process. That is entirely up to the Ministry of Environment in Denmark. I will present lots of perspectives here, and it is expected that the report will be publicly available in the nearest future. But it is, again, not up to me to decide when that happens. Okay, so back in 2020, the former government decided that we needed to implement action on this climate gas emissions from nitrous oxide emissions in wastewater treatment plant. So they decided on a goal to implement a limit value for N2O emissions for all Danish wastewater treatment plants treating the wastewater for more than 30,000 people equivalents. It is a 50% reduction target with an expectation to increase this to a 70% reduction by 2030. The 50% reduction is to be in effect from 2025. So quite close it is. The work that we have done here, we have done together with another consultancy company called Nitrous. It was divided into two sections, a fundamentals section and an implementation section. In the fundamentals section, we cover three areas here. We cover the measurement methods, the regulation methods, and considerations on the actual baseline from Denmark on nitrous oxide emissions. In the implementation section, we include perspectives on guidelines for how to measure and how to control or regulate. We consider also effects of including smaller treatment plants than those treating 30,000 PE and more. And then we consider, among other things, costs and shadow prices of measuring and mitigating to the target of a 50% reduction. So jumping straight right into it, measuring methods to measure accurately. Well, there are two basic principles that we covered, 4 methods and many technologies, but in essence, still few solutions. The overall goal is to, of course, determine the actual N2O emissions. To do that, there are two principal methods, as we see it. One is the process-specific measurements, which include a local, often online sensor or online analyzer, with off-gas sensors or liquid sensors. The off-gas sensors then is often made up of a gas hood and an associated analyzer. Those are process-specific methods. Then we have the plant-wide methods, which in this case we considered two of the methods, the trace gas dispersion methods and the drone flux methods. Both of these methods measure, or aim to measure at least, the actual combined emissions from a whole wastewater treatment plant. And obviously this also covered chimney off-gas measurements from covered plants, which obviously also includes the whole emissions of the plant. So that is the basic difference, that the process-specific measurements often include online sensors at a specific site placed in a local point in the wastewater treatment plant, measuring frequently and online, whereas require a further data post-treatment to calculate or estimate the full plant emission, whereas the plant-wide methods often have a tendency to be more of a spot sample, which is not online, but include the whole plant emissions. Those are the basic differences between the two. Here is shown a typical but high N2O emission profile from a Danish wastewater treatment plant called Avedøre, as presented part of the Varga project, not done by Krüger, but by other actors in the field. And what is clear from this 4-year study is that there is a high dynamic of the N2O emissions of such a plant. This nature of N2O emissions influences the choice of measurement methods, since we require a method that is able to capture this dynamic in order to represent and calculate trustworthy emission factors. That points towards online measurement methods or the process-specific measurement techniques. Another thing here is that also from the same project, it was shown that even though we have, here it's shown 2 separate lines comprising 2 tanks in every line, so 4 tanks total, it is clear that the emission factors measured from these different tanks and lines are not identical. In addition, they did very exciting reduction or mitigation efforts and was able to show an actual reduction by changing the mixed liquor suspended solids in the process tanks. But it just illustrates also that these types of process operational differences also influence the emission factors of the individual plants. Again, stating that not only temporal dynamics are important, but also spatial differences within a plant is important when a true representative value is desired from the emission factor of a treatment plant. To illustrate here the complexity of this, when we have a process-specific measurement, what we do first is to do the measurement in itself. After that, we need to calculate the associated emissions from the one tank. This is due to, even though you use a liquid sensor or an off-gas hood, you still need to measure or extrapolate the emissions from that local spot to the full tank, where the sensor or measurement is placed. You still need to extrapolate to the one tank. Again, you need to further extrapolate this to a full treatment plant emissions. And in that, you need to add knowledge of analysis of the nitrogen load to the plant in order to calculate the emission factor. All of these steps from concentration to emission is associated with uncertainty, but it's important to represent the true emission of a treatment plant. And especially if the goal is to document the effect of mitigation strategies, it's clear that it's important to have comparable scenarios or measurements of the emission factor before and after. Also, if you want to compare between plants, it is important to have comparable ways of doing this when you want to compare. Very basically, even The first question one needs to ask is whether or not you want to apply an absolute or relative limit of the limit value. So is it a kilogram total per year of nitrous oxide that is the target, or is it a percent of emission factor, for instance, that is the target? Further on, for each of the categories, you have various ways of constructing a limit. You can do a fixed limit, which is the same for all treatment plants. We can have a differentiated limit, which maybe have a stricter limit for large plants and less for small, or the other way around. You can have a relative limit that is dependent on previous measurements of the baseline, and then it's a 50% reduction based on that. So the targets are differentiated because you have a different starting point. You could also impose an individual limit that is also corrected for the potential or ease of mitigation for the plant, so that plants that have a large potential of a greater reduction has a stricter limit than those who have a real challenge in doing so because they are overloaded and challenged in capacity, for instance. All of these issues need to be considered before constructing the actual limit value. Again, the target here was to do a 50% reduction using a limit value of that. It makes sense to go further with an emission factor, which would be then the relative limit. And it is also meaningful to have a starting point that is realistic, perhaps starting with a fixed value, and then along the years, as knowledge increases, move more and more towards the individual adapted limit values. But obviously, they also require a higher background knowledge before being able to do that in a fair and cost-effective way. So what is the starting point even? Because the government here was very ambitious, and they stated an ambition to have a reduction of 50% without really perhaps truly knowing what the starting point was. We did thankfully have already a previous project trying to identify or determine the national specific emission factor for Denmark. And in this study, it was shown that we in Denmark have a emission factor of 0.84%, which is lower than the IPCC from Europe in general. But it is not created on the base of a large amount of wastewater treatment plants, but a selected few participating in the project. We tried as part of the project here to extend that data foundation more to validate whether or not this value was representative of the national state as a general. What is clear here from this one is that the black line associated with the 0.84% limit covers or simplifies some diversity between plants. So even though 0.84 might be the right average or starting point, it's clear that this is not the precise value for all plants. So there is diversity between plants. And this also hints on one of the challenges here, that we have an ambition and a target, but we don't really know very surely where we start. So we need more data, and more measuring. But the true motivation to do measurement is that we have a requirement to do so. So it's kind of the chicken and the egg here. What comes first? This regulation could be the approach to start having more intensive measuring in order to create the knowledge foundation that is needed to adjust the baseline and do the right regulation in the end. So also we need, of course, to balance the effort we put into measuring and mitigating with the cost associated with it. So we speculate that there might be two methods to do measurement and control of the emission factors of the treatment plants. We call these the basis method and the extended method. The basic method is in essence that we put only one measuring point in every type of aerated biological process. This would mean that if you can argue that you have 4 or 8 identical activated sludge treatment plants operated in the same way, with the same conditions, with the same behavior, you only need to put a sensor in one. You can then estimate or guess the anoxic contribution of the emission factors of that treatment plant, and no need to do no further additional analysis of nitrogen loading in excess of what is already required by the regulation. A very basic method, primarily designed to increase the knowledge and specify the correctness of the chosen baseline for Denmark. Then there is also the opportunity to do an extended method, which then would require a measuring point in every aerated biological process, and not just every type, but every actual biological process. It would also require a measurement for more precise estimation of the anoxic contribution, and then extrapolation to full-scale emissions. It will also require additional analysis of the effluent in total to increase the precision of the calculated emission factors for the plant. We speculate that this could be done in an approach such as this, where the first year after implementation of this regulation would cover a baseline period, a screening period, where we have the opportunity to gain excess knowledge of the actual baseline, and also gain insight into whether or not there is a large diversity of the emission factors between plants or a small diversity between plants. This is important when we want to calculate the effect of a specific limit value, and whether or not it is able to achieve the overall 50% reduction. Therefore, it also includes the possibility to do a review of the limit value in between or after the first year before going forward. The point is then, with the one sensor in one tank in all plants, if that sensor implies that we have a treatment plant that is above the limit value, it triggers the need for application of the extended method, where the plants need then to install more sensors or analysis in the plant to increase the validity of the estimated full plant emissions. So that is the first step to see, okay, that calculated emission value that is above the limit, is it actually above the limit, or is it a measuring diversity, or not an error, but is it insufficient to describe the true full-scale emission from the plant? That is then, if that is then the case, it also triggers the need for mitigation for that. If the plant is not above the limit value, carry on as before with the basis method to do the limited amount of measurement, but to still have the surveillance and the monitoring to document what the actual emissions are. Along this way, we also created a few rather simple guidelines for how to make sure that the emission factors calculated, the measurements done, and so on, is of equivalent standards between plants, so that we have equally reliable emission factor calculations along the whole country. It includes parts like how to what is needed with the N2O measurements, that is important to register flow, airflow, that's important to calibrate and validate data, stuff about how to do data post-processing, how to handle missing data in the data set, and how to calculate the emission factor. All of that is important to increase the quality of the, in the end, calculated or estimated full plant emission factors. And obviously, the instructions on how to do that will need to be extended, expanded, and refined as we learn more along the way, especially during the first year baseline period. Then this small area, this thing about the small plants, well, in Denmark, it is the case that, that with regards to numbers, 74% of all plants are considered small plants with less than the 10,000 PE, and they treat 7% of the load. So the initial evaluation is here that it is a good choice to start focusing on the 30,000 PEs and above until we learn more on the associated cost of measuring, because the number of small plants is very high also in Denmark. And the amount of the load they treat is rather limited. Then, is it even realistic to reach this level of mitigation? Well, we compiled a list of potential mitigation tools, strategies, activities that could potentially lead to a achieved reduction of the 50%. What we did was that we compiled these into two useful primary options. All of them have positive effect, but which one of them could stand alone to reach the at least 50% reduction? In our opinion, option A and option B are potential ways to achieve this. Option A is a process optimization and online control approach, where a combination of process optimizations and or online control of the treatment plant can potentially achieve this goal of the 50%. And we have estimated a very, very rough estimated price of implementing this in a first process train in a rather small treatment plant of 40,000 PE, and then also additionally calculated or estimated the price for any further treatment train of 40,000 PE on top of that in the same plant. So we estimate here that the three actions related to, for instance, aeration, carbon management, and sludgeate would be able to achieve this 50% reduction. That is the target, and that the price is quite competitive compared to other solutions that require a large capex investment in especially increased capacity of that plant, because that is the other favorite option, is to do capacity increase of an existing plant, and here we estimate that that solutions like MABR or IFAS solutions could potentially increase the capacity sufficiently to achieve this 50% reduction, but at a somewhat higher cost. So to wrap up, we estimate that it is possible in practice to introduce a measurement method and a regulation method that can be brought into play already from 2025 in Denmark. The current baseline we have established here is a good starting point, but it is very essential that it is qualified as long as when the measurement program is implemented and we gain a lot more knowledge of all of the plants that have not so far been measured. The limit value can be arranged so that it is both effective, realistic, and fair. There are reduction measures available that are expected to be able to reduce all of the plant emissions to below the limit value. It also appears that the most can be done at a competitive and cost-effective shadow price. And if all treatment plants above 30,000 PE follow the basis method, measurement capex is estimated to these 1 to 2 million euros, and with a yearly maintenance cost of 0.2 to 0.3 million euro per year, depending on the measuring type. There are, of course, large uncertainties related to this guesstimate. The optimal estimated cost of measuring and reducing nitrous oxide by the 50% offers a potential of a shadow price down to 6.5 euros per ton. That is, of course, the optimistic target, but just to show still. Then on top of this, some mitigations, as chosen before, might even have other substantial added benefits. One could imagine that some of these solutions could also improve the overall treatment performance of the treatment plant by improving the nitrogen removal, for instance, or others like that, or carbon management. Yeah. Okay. Good. Just credits for the team, Valerie and Nitrous participated in this. And then I have this final one because I also promised in the presentation to cover a little bit about the development project that we have here in Korea. And this is because, as you saw in the table before, there are a lot of estimates on the effect of mitigation strategies. And we believe and hope that the combination of strategies here are able to did my presentation stop now, Christian?
No, it's running. I just wanted to, I hate to rush you, but we have a absolute maximum of 10 minutes for the last bit of the presentation. Otherwise, we have no time for questions.
That will be fine.
Yeah,
it's very
fine.
brief. Yeah, no
Super.
Yeah, thank you. As you can see from that table, to achieve the target of the 50% reduction, the effective mitigation strategies are very important. But very limited documentation is actually available on how these different mitigation strategies are able to achieve that over a long-term period under normal operation. Most of the experience we have has been done in shorter term or in dedicated experience with a particular focus on that. But when we need to implement this in normal operation under all of the other targets and goals that a treatment plant has, the challenge is harder. And so we need to have documented effect over long time under real operation. So that is part of the point in this N2O control project, complete control and documented effect, where 8 utilities have combined to do the development of a new type of control and also to document the effect. The point of this is that we have a lot of tools to handle N2O reduction and mitigation, involving carbon management, aeration control, all of the solids retention time, all of these things that are key to the operation of a treatment plant. But it is important to be able to balance these in a dynamic way, continuously optimizing for treatment performance, for energy and OPEX, and also for CO2 footprint. The best way to do that is through dynamic control solutions. Here. This specific control we want to develop focuses specifically on preventing the production of nitrous oxide by gaining control of the speed of the biological nitrogen removal in the process and includes actually DNA analysis as part of this task. The project is a 2-year project where 1 year is baseline documentation and 1 year mitigation and validation year. In this period, we are now currently building the new nitrous oxide artificial intelligence complete control that targets the prevention of production and reduction of emission. And the point of it is to balance these 3 OPEX, compliance, and carbon footprint in a 3-fold cost function with a predictive model. We will soon be starting to do commissioning of the control. Now we have what we call the standard artificial intelligence feature running on most of the plants, and will gradually increase for the control for N2O and then document effect. This is a very this is a good example of dynamics of N2O you can expect in a treatment plant. This is from Avedøre, and as you can see here in orange, we have a saturation here where we have an increase in the concentration. It's associated also with a blue increase in total emissions, and it varies up and down. That is a variation due to aeration. When the aeration is on, the total emission is higher, even though the concentration does not necessarily change. What we can see if we flip a slide here is that we have the N2O production during aeration. It is then persistent and it is not reduced or removed during the 2 peaks around 8 o'clock in the middle of the screen. Between the 2 aerations, it is not removed during denazification in between the 2 aeration zones. So here we have 2 mechanisms that are important. We have an aerobic N2O production have a failure or insufficient denitrification to remove the produced N2O along the way. That is associated also with here that you can see that the N2O is not reduced between aeration. The orange one here is then in the DO concentrations and is not removed in the periods where the DO is low. The denitrification is insufficient, and these are the mechanisms we want to be able to handle all combined in one using these. The very basic control that we have already as part of that upgrade system is that we have a direct N2O control able to limit and reduce the emissions simply by turning on the air if the concentrations is high. It's very simple, but it's also very effective. It is also what triggers a early denitrification phase, enhancing the removal of undesired N2O produced in a previous aeration phase, for instance. What we need to handle still is how do we do nitrification without associated N2O production. And we want to achieve that by gaining control of the specific nitrification rate of the nitrifiers present in the activated sludge. And we do that by combining online control with the dynamic prediction in artificial intelligence models and insight into the DNA and nitrification capacity of the actual plant biology. So we just need to predict the future, control the specific nitrification rates, measure nitrous oxide, and adapt and balance these aeration intensity, nitrification phases, DN phases, all to a maximum benefit of balanced energy consumption, carbon footprint, and effluent quality. Easy peasy. So with that speed talk here in the end, I hope I did not exceed my time too much.
Perfect. Perfect, Mikkel.
Questions in the end there.
Thank you very much for the great presentation. Both parts, of course, extremely interesting. There is a question already from Valerie in the Q&A. For all you others, you can drop your questions in there now. You could have done it before as well, just as a note. But the first question is about CO2 price and carbon taxing, whether that is something that might be planned in Denmark. I mean, just to add on as well, maybe from the Vaga project.
My opinion is that the most effective tool would indeed be a CO2 tax. The challenge with a tax is that it requires an even more precise determination of the actual constant CO2 emissions of all the treatment plants, right? Whereas a limit value is a more soft approach in the beginning, where if you cross a limit threshold, the sanction is take action, do more, implement this additional activity on your site. It's more soft and less challenging for actual measuring, documentation, emission, and so on. But I know that there are considerations to go in that direction, but the feasibility of doing so is still in debate. I think that this limit value will be a good start, and I hope that it will eventually move in the direction of a CO2 tax instead, because it'll make it easier to balance all of the requirements that a treatment plant has today.
Sure. Yeah, I think I would fully agree. And I mean, looking at this shadow price of about €6, I think in the Vaga project they even calculate 1 to 2 euros for mitigating a ton of CO2, which is a very low price for when we look at carbon markets that are between 100 and 200 euros per ton. So then even, the financial incentive is very real if that framework is there.
Yeah.
So I think the potential is big, and it's good to hear that these things are being discussed as well. I have one other question towards the emission factors, and basically asking you to just keep on your process engineer hat for that. From that point of view of pure process control and understanding the process at a specific wastewater treatment plant, do you think an emission factor is even a feasible way to describe what's going on a treatment plant? How would you describe that?
Well, obviously, it depends a lot on how that emission factor is measured. But I do actually have a strong confidence in the use of an emission factor as a comparable unit for plants to measure themselves and each other up against. It is relative to the size and the load of the plant, which is very nice, and it is a parameter that all plants can produce, so all plants can compare, and I think that is the key value of doing so, that we can compare between plants and nations and so on.
Yeah. Definitely. That baselining is very important, I think, for the sector as well.
True, absolutely.
Yeah. Sorry, I'm just finding. Just give me 1 second. I didn't update my Q&A box. Somehow didn't update. Sorry about that. So do we actually have many questions? But we only have time for a few. So let me just see to which one we will pull out. There's a very specific question. Which would you prefer to express the percentage in nitrous oxide emission based on the influent total N or the total N treated? How would you compare these two?
Yeah. So I think that this is an artifact of remembering that not all plants have requirements, or have not had requirements to the effluent nitrogen concentration in their effluent. Some countries do not have that requirement, and obviously for them it is wrong to produce an emission factor based on the N in the influent if they do not have active nitrification processes, for instance. For those plants, it's more representative to have a factor associated with the removed nitrogen. For Denmark, that is not the case, and that is why we only consider the total N influent to the treatment plant as the best representative part of N in the calculation of the emission factor. Also because that this specific one then also covers any return reject water nitrogen load from biogas plants and so on, because that is already part of the incoming wastewater from the very influent of the treatment plant. But I recognize that in other countries with different treatment plant requirements, it might be more useful to use the one for nitrogen removed.
Yeah. Okay. Thanks very much for these insights, Mikkel. Yeah, with that, we will move over to the next presentation, which will be Valerie Sels from Royal Haskoning DHV in the Netherlands. Valerie has a Master in Science from Delft University and has then spent the last 5 years on working on impactful wastewater treatment plant optimization topics. And yeah, I'm very thankful and happy that you're here today, Valerie, and that you're willing to share the insights on what's going on in N2O in the Netherlands. So yeah, the floor is yours. Looking forward.
Thank you, Bastiaan, and also thank you, Mikkel. Very enlightening to have the Danish approach explained in so much detail. So let me hit share as well in order to show you our Dutch approach. So I believe you all should be able to see my slides now.
Yeah, looks very good.
Great. Thank you, Bastiaan. And yeah, let's take it away. In the Netherlands, we are heading also towards an ambitious goal regarding net zero, combined with more strict effluent requirements coming our way in the near future. And this is what I will base my presentation on today. But before before we dive into this, I want you to picture this. As a water utility, your main responsibility is clean water. These challenging times, it might be hard to find a budget for R&D projects that are not directly related to this core responsibility. And perhaps you're already in the middle of expanding your capacity or meeting those more strict effluent requirements, or perhaps it just feels good enough to report your N2O emissions based on the IPCC factor. But what if I told you that the installation of a nitrous oxide sensor gives you more than emission data alone? So we think that it puts the focus, or we know that it puts the focus back on your current treatment process, giving you insight in the performance of your current nitrogen removal, because in the end, that's what nitrous oxide emissions are all about. It also requires you to maintain your other sensors, to pay close attention to your process performance. And that is already a huge win for your current treatment process, and it will show in your effluent results. We need, of course, more long-term measurement campaigns to back this up with the data to really establish this relationship. But we can already see clearly at our clients that the focus on N2O mitigation goes hand in hand with a good effluent quality. This is a win-win situation as it might even reduce the need for those huge investments to expand your current treatment process. It's really about the attention to details. And today, I hope to inspire you not only to unite on a national level, I will talk about the Dutch acceleration research program, but also again to start measuring on site level, because we can all contribute in this road to net zero. So for the Dutch national approach, let me take you along on our N2O journey, so to say. In the Netherlands, we are united with 21 water authorities. You can see the dispersion on the left, and there are about 350 wastewater treatment plants. The wastewater treatment plants are owned and operated by the water authorities themselves, who are public organizations. Fun fact, in the Netherlands, there are even a democratic institutions with elections every 4 years. And now we are facing quite some challenges in the upcoming years. But this is a timeline where I first want to highlight the year 2027, where we have to comply with more strict effluent qualities related to surface water. It's part of a larger framework, and that is quite soon. And for not all, but for some water authorities, this poses already quite some challenges, and there's a lot of focus on this right now. Next to that, we are heading towards the European Wastewater Directive, still in draft, but I believe the effluent requirements are more or less set. So for large wastewater treatment plants, we are heading towards a total nitrogen effluent requirement of 8 milligrams per liter and 0.5 for phosphorus and 10 milligrams per liter for nitrogen. 10 milligrams per liter for nitrogen. So that is something we are heading towards and also prepare our treatment plans for. And then there's the ambition to become 100% climate neutral, so net zero in 2035. Sorry. So that is coming our way, and for the last 15 years, the Dutch water authorities, together with STOA, which is our national research initiative for the wastewater authorities, has been doing research into nitrous oxide emissions. And for already more than, I think now 3 years, the water authorities have been united in a community of practice. And from that, there is this research program established. which will focus on the next, which will run for the next 4 years. So how is this national acceleration program, so to say, or research program, how is this organized? So on the left, you see our 2021 water utilities. And as I mentioned, they're united in this community of practice for nitrous oxide. And from there was a core group formed together with the partners to establish this research program. And there is a financial contribution from our Ministry of Economic Affairs and Climate Policy, but I also want to stress there is a huge investment of the water utilities themselves. Now, what are the objectives of this program? The program is divided in 3 research lines, so to say. And the first one is really clearly to gain insight in our national emissions. Also, Mikkel talked about measurement methods. We'd like to make sure that everyone in the Netherlands is doing the same thing. So yeah, we want to make sure those are validated and clear for everyone. And then really gain an insight on this national level, but also see if we can, again, play with those emission factors a little bit. I think a little bit similar of what Mikkel already showed us. And I will explain this in a little bit more detail later. But we want to see, okay, can we sort of characterize an emission factor, not one for all treatment sites, but specific for a certain configuration or a certain people equivalence, a certain size, et cetera, et cetera. And we like to further understand what process or characteristics or parameters are most influential in order to, in the end, perhaps make a decision tree where you can say, okay, I have this type of configuration, this size, then I can use this emission factor in order to get a general estimation in order to report your nitrous oxide emissions. Then secondly, of course, we like to validate reduction strategies that are most effective for the Netherlands and for the type of configurations we mostly have, and also understand what is the impact on effluent quality and also electricity consumption and others, so to say, both on design criteria and also control strategies, the advanced process control that also we already talked about. I will, for this presentation, focus mostly on the first part, but feel free to ask questions about the second part if you want to. So this might be a little bit of an overwhelming slide, but this is the planning of the program. As I said, the whole program is 4 years. On the left-hand side, let me get the laser out. So there is the first track or research line where we want to gain the insight in the emissions, and the second track where we are looking to reduce the emissions. Then there are 3, let's focus on 2 groups established of wastewater treatment plants, Group A and Group B. Group A is the group of wastewater treatment sites that have already been measuring for more than a year. They're kind of the front runners in the Netherlands, and there is already a lot of data available for analysis. So currently this data is being gathered, and from there we already like to make a start with this decision tree on emission factors that I just talked about. Then secondly, that's about to start or is already well underway, is the second group of wastewater treatment plants that we selected to make sure that we have a broad representation from the Dutch wastewater treatment plants, and we'd also like to make sure that we include other parameters and measure other parameters think of nitrite data or other types, maybe even DNA, that you can also measure to maybe also gain further insight in the process, but also maybe find kind of proxy parameters that you could measure instead of nitrous oxide with the sensors. And then lastly, there is also a group C. The size of this group has not really been determined yet, or as that's more further into the program, we will learn and learn as we go. But the idea is that they will estimate emissions based on those process parameters that are defined with group A and B, and maybe not necessarily measure the nitrous oxide directly. So, as I said, group A is already well underway, and with group B, we wanted to make sure that we have this good representation from the Dutch wastewater treatment plants. So we looked at all those 350, more than 350 treatment sites in the Netherlands, and we looked at, okay, what can we differentiate them on? So on the left-hand side, here you see all the Dutch water authorities. Then this is group A, so the locations that's already being measured. You see that a few water authorities are already a little bit more active, and in group B, the other water authorities need to also will also start or follow. And this total set of sites that will be measured will come to a total of 51. So that's quite an impressive number, so to say. And how did we determine, or how did we make this selection? So I already talked a bit about this emission factor and how we'd like to further make it more specific. In the community of practice these last couple of years, together with STOA, there was this simple risk model developed. Of course, currently the emission factor is calculated based on the incoming nitrogen load, but we believe that it's very useful to look at your nitrate and ammonium concentrations actually in the effluent to determine whether there's a low or a high risk on N2O formation in your treatment plant. So that's basically the first step. Okay, categorize the wastewater treatment plants in these two categories. We have adjusted this model already once. There's a STOA report on that for whoever is interested. And we hope to further update this model. But after the categorization, we looked at the influencing factors like configuration, reactor type, nitrogen load, etc. And we were also already trying to find correlations or trying to explain the differences between those low and high risk treatment sites. So we looked at more items actually. So this is a simplified representation of a wastewater treatment plant, and we found in our analysis that of all these different elements, doesn't show my animation, sadly. Okay, doesn't matter. So our analysis showed that actually the type of reactor, so whether it's a mixed or a plug flow reactor, has an influence whether a treatment site is low risk or high risk. The type of aeration, we weren't really sure. That is something we'd have to look into more when we get more data. Also, the nitrogen loads, was striking that there's a lower nitrogen load was mostly found with low risk treatment sites, and then also the total nitrogen in the effluent, so a better, so to say, again, better effluent quality for low risk treatment sites. Now, we ended up with 4 categories of treatment sites. That was wastewater treatment plants smaller than 100,000 people equivalents, and treatment sites larger, including sludge digestion. And then for both of them, we have low risk, high risk, low risk, high risk categories. And on the left-hand side, you see the nitrogen sludge load. And on the right-hand side, we see the total nitrogen in the effluents. If I focus on the graph on the right, we can clearly see again that a better effluent quality also correlates to the low risk treatment sites, and again, a higher effluent quality for a higher risk. It's interesting also to see that the treatment sites with, in general, the larger treatment sites, more people equivalents, tend to have higher emissions in general, and this is also what we saw in the model. And now this graph is again, this is based on total effluent. We see the same trend in sludge loads, but of course also for these larger treatment plants, there's even more factors into play, like we saw on the previous slide, with liquor returns, might be more dynamic. So typically it gets a little bit more difficult and a little bit higher risk for nitrous oxide emission. So all in all, we ended up with those 51 wastewater treatment plants, and yeah, we are well underway with the measurements, and we are hoping to actually further update this graph. So already in the Global Water Research Coalition report from 2011, it was mentioned that a good effluent quality goes hand in hand with a low emission. We also, of course, obviously, we need more data, but we can see a cautious start based on the Dutch data that we gathered so far. And in the graph, you see the emission factor on the left-hand side and the total nitrogen effluent quality, so not removed, but the final effluent quality on the x-axis. So yeah, the Dutch acceleration program is now gathering the data. Then data analysis from Group A will start before the summer. Group B are installing the sensors on the remaining site, and as I said, the program is expected to run to 2028, with hopefully, well, I'm sure a lot of data coming our way. And yeah, with that, I'd like to conclude. And I lastly wanted to thank Bastiaan for giving me this podium. But I also like to emphasize that especially this Dutch National Acceleration Program is a joint effort from all the Dutch water authorities. It's supported by STOA, the Unie van Waterschappen, the ministry, and all other governing and knowledge institutions. So it's a big thank you to the sector really for doing the right thing, even though, unlike in Denmark, there's no binding legislation yet in place. And we as RHEHV, we continue to support the sector through our consultancy services, our technology products like Narita and Ephira, and digital products like Advanced Process Control. So if you'd like to know more, please reach out and let's continue to enhance society together. Thank you.
Thanks very much, Valerie, for this fantastic presentation. And thanks for sticking to time as well. While waiting for questions to drop in, there's one question that I like to ask you. If you can expand a little bit on, well, how in detail are the measurements being done practically in the Netherlands, and also how that data is being gathered. I know there's a common data platform for all the water boards in the Netherlands, whether that plays a role, and yeah, what are the feet on the ground doing, let's say?
Yeah, that's a great question, Bastiaan. Thank you. And I think it's nice you mentioned also the platform we have in the Netherlands. I have a slide on that. Are you able to see it? Because I hid it in my original presentation. Okay.
Yeah.
So like you said, indeed, in the Netherlands, data from our sensors, and we typically have a lot of sensors in our biological treatments, like ammonia, oxygen is pretty standard, and also for the treatment sites that we are including in this research program, we also would like to really add nitrite or nitrate. There are still discussions about it, how to make it feasible for everyone, and also whether we want to include maybe real-time ammonium measurements on the influence, stuff like that. But indeed, all this data is gathered in a platform that I think almost all of the water authorities used, and the data is eventually it's summarized into a database, which is open access. Everyone here can access that, and there you can find a summary based on yearly values on how a treatment plant is performing, what the load is, et cetera, et cetera. And we are hoping also to, in time, include, of course, the nitrous oxide measurements there. And coming back to your question on how there's measured, how the measurements are performed practically. So as part of the research program, there was a monitoring protocol shared, which is a living document, and we will also update over time. But there it was per configuration, it was advised where to place the sensors. But I think for most configuration, we said at least put 2 sensors in your site, at least one in your aerobic and one in your anoxic zone. Play around with the location in your lane in order to find the most representative concentration. And then the whole, I'd say, challenge of data gathering starts. And this is also something, I mean, the water authorities have been doing that for quite a while now for themselves. And now the challenge is to get the data across and shared with the program. And that is something we will start at the beginning of summer.
I think it's really inspiring to see and hear what is happening in the Netherlands, and knowing that this is built on a long experience, of course, but also seeing that it has started many years ago already without this government activity around the topic, something coming out of the ambition of the water boards. I think again and again is very impressive to see that going. The ambitions of the water boards. Thanks a lot, Valerie, for expanding on that. And I think with that we can move to the next presentation, which will be Bharani Sri. Just waiting a second for him to come up. Fantastic. Hi, Bharani. Bharani is the process emission monitoring lead at Severn Trent in the UK. To my knowledge, Severn Trent has, among the water companies in the UK, the longest and broadest measurement campaign of nitrous oxide on their treatment plants. And so, for that reason, very, very happy that you're here today and that you're willing to share some of the learnings and experiences from these measurement campaigns. Thanks a lot, Bharani. The floor is yours.
Thanks, Bastian. Morning, everyone. Thanks for having me here today to share some of our learnings from our monitoring program. My internet's being a little bit spotty today, so I will turn the camera off fast before sharing slides so we don't drop off. Fantastic. Thank you very much. Right. So I think I'll start off with a little bit of a background into the UK water industry and go on to Severn Trent and what we're doing in this space. So in England and Wales, the water and wastewater services are provided by privately owned companies which operate under a regulatory framework set by various government departments, such as DEFRA, the Environmental, Food and Rural Affairs Department, Ofwat, our economic regulator, and the Environmental Agency, along with a suite of other department that regulates us. So within that space, Severn Trent, we are a water and wastewater company that serves around 8 million customers in the Midlands and Northern Wales. And our journey towards net zero started a little while ago. But to avoid talking through all of these, I will focus on 2019 onwards when we made our triple carbon pledge. And the triple carbon pledge we made was by 2030, we will be net carbon zero, 100% renewable powered, and have 100% electric vehicles where the technology permits. And my focus within the space is the initial one, the net carbon zero, the scope 1 emissions. So if you take a closer look at our direct scope 1 emissions, around 80% of it comes from nitrous oxide and methane from our sewage treatment and sludge treatment processes. The raw material that turn into these greenhouse gases comes from people's homes into our treatment works. We can't really control that, but what we can do is work towards minimizing the conversion into the greenhouse gas and its subsequent release into the atmosphere. And over the past 3 years, we've been widening our monitoring to better understand the source of these emissions and explore potential mitigation opportunities. So I'd like to focus on nitrous oxide here for this meeting rather than methane to keep things interesting. So with nitrous oxide, the activated sludge plants appear to be the biggest source of nitrous oxide emissions, and the way we are currently monitoring that is by using the dissolved N2O sensors from Unisense. We place them approximately 1/3 and 2/3 of the way into the lane, and then we measure a number of other parameters to enable the conversion from the dissolved nitrous oxide into the gaseous emissions. And a couple of practical learnings that we've had in setting these up on our site is definitely send all the measurements to the telemetry for faster and more streamlined calculations, but more importantly, having that live access to the data has really helped us identify some of the issues early, whether that be sensors going offline or any other parameters, not just any sense, any airflow or temperature or anything like that, having any kind of problems so we can spot them early and get them rectified so we're not losing valuable data. Especially with something like N2O, which is incredibly seasonal and diurnal. So it's important to capture this information. And then also having this data in a single place, what we call our data lake, has enabled us to use things like machine learning to get better insights from our data, which I'll talk about a little bit more further down. And then we've chosen to express our emission factor in terms of measured nitrous oxide in the lane, per measured ammonia going into the lane. So that's your settled sewage ammonia. So the part of the reason for this is because we, as a company, don't have many TN permits. I think we have a single site out of the 900 something sites that we have, whereas most of our large sites will have online ammonia monitors going into the ASB lane. So we had essentially measured load as well as measured N2O, so we were able to work out a emission factor that's measured versus measured. So when we first started monitoring, so this was back in 2021, we installed our monitoring in one of our innovation sites called Spurnell Sewage Treatment Works, and we were able to take this measured emission factor and compare it to the current industry reporting methodology, the Carbon Accounting Workbook. And we were able to see that the current methodology was at risk of undercounting significantly. So we made a decision to report our emissions directly, where we took the emission factor and applied it across the 940-something wastewater treatment works that we have to highlight the scale of the challenge. But one of the questions that we kept asking ourselves is, how representative is Spernal, that single site, approximately 200,000 population equivalent, to the remaining sites that we have, which is a broad church of some really large works, around 1.6 million population equivalent, to some small, tiny works, which will be very 1,000 PE. Off the back of that, we took a decision that we will roll out this monitoring to an additional 8 sites that now comprises a total of around 42% of our total population that we serve. So those are naturally going to be the big sites, but at least those big sites we can monitor, so we have more confidence in our overall emissions reporting. So that has just gone live. So we have just under a year's worth of data for most of them. So we should be in a position to share that fairly soon, but we'll look at Spernal in more detail where we have a longer-term data set. In addition to the activated sludge plants, we've also been conducting a campaign of flux flux measurements around our wastewater treatment networks. And what we generally find is most of the assets, like the settlement tanks, the Cape pads, they are fairly low in emissions, except for our side stream liquor treatment processes, the Anamox plant in one of our sites, which has been identified as a key emitter. So one of the recommendations further down is that might be the other asset that we consider directly monitoring over a longer term. So if you wanted to look at some of the results, I think this type of trend, I'm sure a lot of us have seen in the past. So what it's showing is it's the different financial years. So that is April to March, and then we've been monitoring over a 3-year period. The red line is just this financial year, so that shows you what April and so far in May looks like. So that's 3-4 years of data, along with the 4th year of a little bit of data. And the main things I want to kind of draw out of these is that seasonal pattern, which I think a lot of us are expecting to see these days. And the important point there is, yes, there is a seasonal pattern that seems to happen around the spring, early spring time. But that itself does move around, so the bugs don't have a calendar, so they're not always going to go on April. So the first year we monitored, that was in April when we found the biggest emissions. However, since then, that has moved around a little bit to happen slightly earlier. And interestingly, in last year's monitoring, we didn't really see much of an emission spike. That's the green line, where we kind of saw a little bit around June time, but it was fairly muted compared to some of the previous years. And interestingly, this year appears to be following the same trend. So this is without us making changes to the monitoring. So we've not moved it, or we've not increased the load or changed any of the site processes. So it's really interesting to see that the same site, same setup is resulting in slightly different emissions year on year. Other than that, it also doesn't appear to be load driven. So I've normalized it for load. So this is our emission factor month on month. And you can see the same trend is observed again. So it's unlikely that this trend is load driven necessarily. It's more likely something to do with temperature, where we've seen some literature coming in as well. That indicate there is likely a good amount of correlation, and it's also supported by some of the machine learning work, which I'll talk about in a second. So that's our main emissions mass trends and the emissions factor trend. So like I mentioned earlier, we had originally baselined our company emissions based on a single site, which is this site. However, we then decided we needed to monitor more sites over a longer term period to better understand if this factor is going to hold, or if that is something that you'll have site level differences. With the data that we've been able to collect so far, I think we can make some comparisons. I've not got them in the slides here because it's not the full years for all of those sites. But what we are able to see is there are site level differences. So it's important to monitor the broad range of processes that your company might be implementing at your sites to get a better understanding of your emissions. So the other part is, one of the reasons to get the data onto telemetry and collect over a longer term period is you can start doing some really fancy stuff with the modern tools like machine learning. So one of that is soft sensing. So the concept here is building a virtual sensor using machine learning models, where we've trained it using 3 years of data collected from Spernal. I said 3 years, it's approximately 80% of that 3 years. So the 80% of the data is used for training, and the remaining 20%, the model training process does not see. We just test it. It's just used for testing. And the idea behind why we want such a thing is in the short to medium term, it's used to populate missing N2O data. So if you have any downtime because the sensors are offline or something's happened, we're able to fill in that using a more dynamic process that is accounting for the other variables that's happening on site, rather than something just using the mean value, for example. But long term, what we envisioned is could be more of a process that could become a soft sensor for sites that don't have direct monitoring. So, like I mentioned, we have around 940 sites, and not all of those sites, with the best will in the world, will be monitored directly. And therefore, having a tool like this could help us fill in those gaps for the sites that won't be monitored directly. Also, the feature value that's going to be chosen by the machine learning model can help us identify potential control levers for process optimization and feed into any potential trials for asset optimizations. On the bottom right, there's a trial that's currently underway at our largest treatment works to test the DO optimization, or dissolved oxygen optimization, as a way of reducing nitrous oxide emissions. So hopefully that results in some tangible benefits that we can share with the wider community in the future. And the final one our data scientists are excitedly working on at the moment is to create those virtual trial environments to test out concepts and ideas before we have to build expensive test sites in order to understand what the benefit might be before we even get there. The top right, there's a graph. So this is our first stab at the machine learning model, and that's the predicted value, the 20% predicted value on the x-axis compared to what we actually measured during that time. We initially got very excited and carried away with this, thinking, yes, we've cracked it. But the main thing is that's too good to be true. So essentially, we introduced a unfair advantage to the model, because we got it to train using a random 80% of the data, and then got it to predict the remaining 20%, which again therefore was random as well. And the unfair advantage we had given the machine there is we know that the N2O emissions has a seasonal and diurnal pattern, and the machine also learned that. And when you're getting it to predict random values, it most likely knows what came before and what came after, so it had a very easy time predicting it. So we scrapped that. We said, okay, let's not do that. Let's do something slightly different, where we got it to where we trained it using the first 80% of each quarter of the financial year, and then got it to predict the last 20% of that quarter. So this way, it does there's a longer period where it doesn't know the pattern or the trend line. So it's more of a challenge for it to predict. But what we found is it's not 1% 1R squared near perfect correlation. What we found instead was it is generally on the ballpark. So the black trend line is the data we trained it with. The blue and the red, it never saw. So blue is the test values, where we didn't show it the data and got it to predict that numbers. And then generally it seems to be on the ball at predicting it. So I think having a soft sensing model as a proof of concept, I think we're there. We think it's something that's definitely feasible. However, we are constantly tweaking the system to make improvements, and we think this will only get better as we feed more and more data into the system over a longer period. However, the learning has definitely been this is valid for Spernal, the site where which data was used to train the system. It's not likely to work for any of the other sites. And at a conceptual level, creating a general machine learning model that will work for all sites may be possible. We don't really know, but may be possible, but only if we are able to feed in this level of data into a machine learning from across a number of different sites, and then maybe with enough data in the future, maybe something like that may be possible. But at this moment in time, we don't think we're going to be there yet. The middle plot, that is the B-form plot. So this is the granular level of how each of the drivers that we're measuring on site leads to the the N2O prediction that is shown on the plot on the left. So I picked out two examples here. So what we're trying to show here is how the features interact with the prediction, the SHAP value for N2O. So the first example is you'll see the blue color there is the low feature value. So if you pick temperature, that means lower temperatures, colder temperatures, and if you pick, the red will be the higher temperatures. So in the first example, it shows having lower temperatures leads to a higher SHAP value. So on the right-hand side, that's the positive SHAP values, meaning you have higher N2O production according to the model when you have lower temperatures. And then the second one is the opposite, which is when the anoxic ammonia is high, it leads to higher N2O estimates because it's got a positive SHAP value. I've already shown you what the zone 1 is, just to keep the slide simple. Otherwise, it's just going to get too busy. But we have there'll be a similar plot for the zone 2, which is our second pass of the ASP lane, but very, very sort of similar observations. The important thing to call out in this type of modeling is its game theory. So when I say when you have a low temperature, you have high N2O, it's not necessarily a one-to-one relationship. The game theory is all about how the different variables interact between themselves to result in a final number. So the SHAP B-form plots are useful to kind of tell you what are your key drivers, but it's not a one-to-one relationship where you control one, and it will definitely affect your N2O emissions. So in conclusion, just to cover off some of the main learnings from our monitoring for anyone that is looking at rolling out some monitoring themselves, so you can learn from our mistakes. So dissolved N2O sensors, they provide some really useful process level data, but they do require close monitoring. The continuous monitor helps us understand the process conditions that give rise to N2O emissions and potential options for mitigation. The probes can be sensitive to mechanical damage. I think we've broken a couple when we are trying to clean them or service them. And the system is also sensitive to fluctuations in temperature. I'm sure Mikkel has talked about it, and Dustin has talked about it in the past as well, with the plus or minus degrees calibration temperature playing a very important role in what we actually measure. So it's important to have this data online. So again, you can see that fluctuation and hopefully calibrate it before you start losing valuable data. In terms of the measurements, so like I covered in the earlier slides, we know there's seasonal variation and we know there's diurnal variation. I think that's pretty well documented so far. There's also a high level of spatial variation. So we are currently monitoring in 2 locations in the ASP lane. And we used our flux monitor hood to move around the ASP lane to get a better understanding of how that your emissions hotspot moves around. And what we found is there is a lot of spatial variation, especially as the load changes throughout the day. However, if you are able to monitor in 2 locations continuously and know how that relates to the process conditions, having this spatial variation may not be a deal breaker. We just need a long-term monitoring data and have a better understanding of how that variation changes to factor that in eventually. But at the moment, having these monitors in to give us process level data has been really valuable. Variation between sites are fairly common. We've been monitoring multiple sites and processes, and we're finding that there are variation. So if you're doing the same, it's something that's worth doing. Year-on-year variation also exists. So we need a long-term data set to understand what normal is. So Stokholm had 3 years worth of data, and even then we're still starting to see that variation. I think a much longer data set is likely needed to understand what normal really is, so we can get an emission factor and apply it to either this type of processes or these type of sites. In terms of major emitters, activated sludge is definitely by far the biggest source of emissions from our works. However, the side stream liquid treatment plant process are also a significant source and is important to monitor directly. Soft sensing appears to be achievable at site level, and the improvements will only come as we feed in more data, but more longer term data for multiple sites are likely going to be needed to create a more generalized models. I'm not quite sure what I was trying to say with that third bullet point, but I think it's likely something to do with the drivers that we identified using machine learning, it's important to know that that is a data-driven model. That's not mechanistic. So we can't say if you just jump back into the chat. So we can't say if the rolling airflow, for example, if you pick that as one, we can't say high airflow would always result in high N2O emissions. It might be a knock-on impact. So you have high anoxic ammonia. That might mean your airflow gets turned up more to get rid of it, and then the machine thinks if you have high airflow, you have high N2O. So it's important to take it for what it is. It gives you some of the indications as to what some of the levers are, but we need process scientists to look at that to inform us of what's actually happening in the process, so we can devise trials off the back of it. So this is not the be all and end all. It is just another tool in our toolbox. In terms of reporting emissions, so this is new for this year. So like I mentioned, initially we reported our emissions by taking an emissions factor from a single site and applying it across the entire board. However, we then learned that there is variation between those sites. So what we have decided to do this year is we report emissions at a facility level. So that's IPCC Tier 3 level, where we have a good financial year's worth of data to report for that year. And we supplement this with the IPCC Tier 1, the global factor, for sites where it doesn't have the year's worth of direct monitoring data. However, when we compare the IPCC number with our own, we've monitored over the last couple of years, what we find is it's likely the IPCC is overestimating a little bit, in our case at least. Therefore, one of our suggestions or recommendation is we do need to explore building process level or country level factors or IPCC Tier 2 to replace the global factors to help with improvements in sector level reporting. So that's pretty much it. So it's a quick tour around our current learnings from monitoring. Hopefully that's helpful for anyone that is considering doing some monitoring yourself.
Fantastic. Thanks very much, Bharani, for very concise and very in-depth presentation. Very interesting insights. Thanks also for the note on how important good maintenance and calibration of the sensors is. Only a well-maintained sensor, of course, can give useful data. So I also can see that there is a few questions in the chat or in the Q&A. So I'll just pick the first one. Maybe you can shortly comment on the flux monitoring hoods, whether you can recommend a supplier for this type of measurement.
So the supplier that we use at the moment is Lycor. It's their smart chamber and the LI7820 gas analyzer. We're also currently testing Aries, their gas analyzer, but I haven't got any news to share on that front yet. But maybe I can follow up off this call just to see if they're quite comparable and easy to use. But the main one that we're using at the moment is just jump into the picture, is the Lycor gas analyzer in a float that we made with some loft insulation.
Yeah. I think one very important thing to note on that is also the size of the area that is taken in, of course.
Yes.
There was a question around the dissolved sensors needing to be underwater. That is, of course, true. They need to be fully submerged in the water to feel the actual water temperature, as is described in the manuals as well. There's one question that I like to ask, a bit more, let's say, crystal ball kind of question, a bit more high level, looking at what is happening in the UK with the specific assets also as they are. Can you give your best estimate, best idea of what will happen in the next years? We know that a lot of the water companies, almost all of them, have some sort of N2O programs running. Do you think it will stay with the water companies? What role will the regulator play? Maybe you can give your best bet on this sort of area.
Thanks, Bastian. That's a tricky one to answer. So like I mentioned, in the UK, we have a economic regulator, Ofwat, that will be playing a key part in some of this as well. So currently, all the water companies in the UK are going through their price review, and where we submitted our plans for our next 5 years of investment. And the regulator will review that and either allow us to charge our customers a bill, which will fund the investment, or not. So over the last several years, we've been making a case to say that the process emissions in the industry is a critical challenge for us to tackle as part of UK's net zero ambitions, which is the net zero by 2050. And as a result, we need to consider how we are monitoring, reporting, and therefore be able to evidence any productions. The industry currently uses the Carbon Accounting Workbook, which is a standard set of emission factors, which is applied to the population served by each of the sites. And starting in 2022, we changed our reporting to publish our direct measurement-based numbers. And then the feedback we got was also to include the Carbon Accounting Workbook as a comparison, so we can be benchmarked against the other companies operating in the country. And then that still appears to be the case. So we'll be continuously reporting 2 lines. One is our measured number versus our the Carbon Accounting Workbook number. The measured numbers has always been higher consistently year on year, and we think the direction of travel would be improvement in the Carbon Accounting Workbook factor. So we think it may be to a more country-specific updated emission factor rather than report what we measure, because I think that will make it quite tricky to compare one company against the other. Although the challenge there is we would still struggle to demonstrate benefits using any emission factors, because how do you do that, right? If you have an emission factor per load, then the only way you're going to be able to reduce the emissions is by treating less sewage, which is not something that is feasible. So it's still a hot topic at the moment, but likely our direction of travel is emission factors in the near future, with us making a case for why direct emissions monitoring is required to be able to demonstrate real progress in the space.
Yeah. Okay, thanks a lot for expanding on that. And maybe it's good to note also that there is a community of practice in the UK that is regularly meeting, I think, and discussing on this topic. And I think that might also play a role. Don't you agree, Bharani, in forming this direction of travel?
Yes, definitely. So yeah, I should have probably mentioned that first. So if you do have a community of practice, that includes all of the water companies that operate in the UK, and yeah, some of the learnings from their own monitoring is all fed into the same process to enable improvements in how we as a country approach this.
Yeah, that's great, and I think that's something that a lot of countries can learn from. That this approach, community approach, is really the best way to learn the most in the fastest possible way. Yeah. So thanks very much, Bharani, for answering the questions, for a great presentation. I will close now with a few poll questions and move on to that. So I'll just take over the presentation and organize myself for 1 second. If you could just turn off the mic, Bharani, for now, that would be great. Thank you. So yes, as a last point on the agenda, we have a few more poll questions that we like you to answer now, also with the knowledge that you have gathered in this webinar, hopefully. Well, the first one is, if you were to design a measurement campaign of nitrous oxide across your own company, wastewater treatment plant where you're working, what would be the 2 most important factors in designing this measuring campaign? If you can have a look at that and give us your input, that would be great. So we have a good number of responses coming in. See that the leading is, well, not fully clearly, but the leading response is the applicability for process optimization. So actually being able to use the measured data for reduction in nitrous oxide. I think, yeah, most practically, that is what we all want to do. Measure the emissions and then be able to act on them, reduce them. Of course, as we want to reduce the climate impact of our wastewater treatment. And then following up on that, naturally, I would say the accuracy of the emission accounting when you're reporting, and price and setup and ease and use seem to be very important as well, and about equally weighed. So thanks a lot for that. That's very insightful. And with the next question, we want to look at the political or the sectorial discussions in your specific region. Are the water authorities or the local governments or the sector, water sector organizations discussing the topic of process emissions at all? Is it a topic at conferences and similar, or is there already even political discussion about that? So please give us your answer there as well. I can see that's a very clear yes until now, which is very good to hear. We're shifting a little bit. There's a few where it's not happening, but it's expected in the future. But I think that is a very clear one on the yes, on the answer, which is very good news, I think, as yeah, the world is advancing towards the yeah, reduction of our direct emissions. One more personal question coming here. When would you be expecting to be working with nitrous oxide measurements? Either yourself planning a measurement campaign, leading a measurement campaign, or being involved in a project where nitrous oxide is measured and potentially mitigated. That would be very interesting to hear what your feedback is on that. Seems most of the people, at least on this webinar, are already actively involved in measurements themselves. It's almost feels like that's the same percentage as on the last questions. So there might be a strong relation between these two, which makes a lot of sense. Yeah, that's very insightful as well. I'll move on to the last question, which is yeah, basically designed to give us your feedback on this webinar. How did you find it? Maybe show your appreciation to the presenters as well. So you can just free text write anything you like into the text box here. Fantastic. Well, it's very nice to read these things, of course. I know we all put a lot of work in preparing this, so I also want to thank my great colleagues, the great team that makes this whole thing possible. It's definitely not a one-man show at all, and it's great to see, yeah, this active community of wastewater professionals joining together and sharing the insights very openly to move towards reducing our climate impact. So yeah, my deep thanks to the presenters today and to their companies that they were able to share their insights. And thank you all for joining, of course. It's been a very good turnout on the webinar. We will be attending a lot of trade shows in the next time. So if you're in North America, you can find us at WEFTEC and at IWA in Toronto. So please drop by in case you're there for a one-to-one chat. And also a reminder, if you're not in these areas, we also have more trade shows going on and other activities. it's a good idea to follow us on LinkedIn, because there we talk about all our activities, and you can stay updated on the topic of nitrous oxide emissions. Well, finally, if there's any open questions, feel free to write to me. Also, I can lead you on to the presenters. You are of course also welcome to write to the presenters directly. They all have their email at the end of their presentation, which you will get by email together with the uptake of this presentation of the whole meeting. So yeah, with that, thank you very much for attending, and wish you a great rest of your days, and I hope we'll be in touch in the future. Thanks very much.